So I'm glad you guys are all here. I hope you have your PowerPoint notes. Please remember, this is a separate set of notes from the first set of notes in this unit of solutions. All right, so let's go ahead and go there. We are going to be talking about something called colligative properties. Colligative properties. Let's start out by letting you guys review a few things that perhaps might be good to do. And these have to do with the properties of liquids. All right. So remember that essentially in a liquid, the particles, whether atoms or molecules, are closer together than they are in the gas state, as you can see here on the picture on the right. But they are not fixed in position like they are in the solid state. So in other words, liquids have a kind of like an in-between type of physical state between the looseness of the gases and the rigid organized structure of the solids. Now, some of the properties that we've studied regarding liquids have been vapor pressure, boiling point, well, freezing point. And let's review a little bit about vapor pressure because that's going to be the lead into today's initial topic here. So let's say I start with a liquid in a closed container. You remember this picture we saw earlier, right? At the beginning, on the left there, some of the molecules on the surface begin to vaporize. That's because the kinetic energy distribution is random, and sometimes they have more kinetic energy than what is required, or that one is limited by the attraction forces with the other molecules. So they vaporize. Later on, gas molecules will collide with the surface and get trapped there if they don't collide with enough kinetic energy. Until at the end, you have what we call a dynamic equilibrium, right? This is when the rate of vaporization equals the rate of condensation. Don't forget, it doesn't mean that you have the same amounts of molecules in each state. It just means that the rate at which they're interconverting is the same. And so you have a steady concentration of molecules in the gas phase. If instead of a simple closed container, we had something like this, right, where we attach a U-shaped glass tube with a column of mercury in it, in the beginning, because you have essentially empty space above the liquid and above the mercury, the two sides of the mercury column stay the same. But as liquid begins to vaporize, those gas molecules exert pressure on the mercury and push it. Since there's nothing to hold back against the mercury on the right side of the U-shaped tube, the column of mercury gets displaced, and we can use the difference in height between the two sides of the column of mercury as an index of the equilibrium vapor pressure. Now, this is not the way that we did our experiment that you guys turned in a lab report for when we were doing the vapor pressure of water at various temperatures. We kind of did a different type of experiment and perhaps less accurate than the one that is shown here. But this experiment we just saw here before is how you build a table like this one that shows you the vapor pressure of water at various temperatures. And I don't know, I had to point this out just because I had to. Notice one of the points that we made in the experiment was that we make an assumption that at 0 degrees, the vapor pressure of water is 0. And you can see that it really isn't. It really isn't 0. There is no complete, what do we call that, devaporization or unvaporization of water. But it's not a big number. It's not a big deal, all right? I just wanted to show you how this table is actually built. It is not with the experiment that you guys studied in your lab report. Now, we also have another property called the boiling point. We said the vapor pressure depends on the temperature, right? And if we build these famous vapor pressure curves, we can tell the difference between different kinds of substances. And we said that the temperature at which the vapor pressure equals the pressure of the atmosphere is the boiling point. In this case, we've drawn a line here across the 1 atmosphere pressure because that's the standard pressure at sea level. And the temperature at which the vapor pressure curve crosses that horizontal line, that temperature is what we call the normal boiling point if it's 1 atmosphere. But of course, we can have boiling points at different uh, pressure. So if the pressure on the outside is higher, of course, the boiling point is going to be also higher. And remember that the difference between just simply the vapor pressure and the boiling point is that the vapor pressure relates to the vaporization of liquid molecules that are coming off of the surface of the liquid. But when you reach the boiling point, all of the molecules in the liquid sample are capable of equalizing pressure with the outside. And so they all have equal chance of vaporization. That's why you see the bubbles emerging from a boiling liquid, in this case, specifically water. Okay, now on the other side of the spectrum, we have the freezing point. And this one we study typically with what we call cooling or heating curves. Remember, freezing means the conversion of a liquid to a solid. And this is a typical type of curve or graph that we use to describe that. Again, as we remove heat, notice that the temperature starts dropping, right? And you can see the different states here as you go from gas to liquid to solid, right? And then we said that what is happening in terms of energy, because remember that once we introduce that actor called energy, we said, you know, every type of physical or chemical change that we observe has a companion change in terms of energy. So in this case, what is happening as you go from the liquid into the solid phase, as you decrease the temperature, the average kinetic energy is also decreasing. As the average kinetic energy decreases, now the molecules become fixed in position because now whatever intermolecular forces there are not having to fight against a higher kinetic energy. And so the molecules kind of settle in place, and the temperature at which this dynamic equilibrium occurs is called the freezing point. We typically identify it as a flat part on the cooling curve here, where the temperature stops decreasing, because at that point, the energy you're removing is not being taken away from kinetic energy. The energy is being removed so that the liquid can become a solid. All right. Cool. So all these properties we studied before, and make sure that you guys review everything about intermolecular forces. In particular, I saw a lot of mistakes on the quiz in terms of understanding what we mean by a hydrogen bond. I want you to go back and please study that out, okay? I need you to be kind of like on top of what is a hydrogen bond and what types of interactions are being broken when you, let's say, turn a solid into liquid, a liquid into gas, or when you mix things and you have to form new interactions between solid and solvent. Please make sure specifically you understand those kinds of intermolecular attractions, all right? Okay, so everything we studied so far has to do with pure substances. But what if I'm working with a solution instead of a pure liquid? And of course, we're going to be talking here about solutions where essentially the solvent is a liquid and the solute might be a solid, it might be another liquid, all right? So let's say I'm dissolving, like on the right side here, a salt in water. Remember that we said that a solution is a homogeneous mixture with special intermolecular forces present. The solvent is the component present in the larger amount, and the solute is the component that is present in the smaller amount. Don't forget that in our model, what we said was that there are three types of interactions that we had to deal with, right? We had the solvent-solvent, And the solute-solute interactions, those are the ones that have to be undone. And then you have the solvent-solute interactions. These are the ones that are going to be formed. All right. So what are colligative properties? Very important. These are properties that depend only on the number of solute particles in solution, but not on the identity of the solute particles. So essentially, colligative properties are physical properties of solutions, and they depend on the amount of solute that's in there, not the identity of the solute. Here are our 4 categories of colligative properties: vapor pressure lowering, boiling point elevation, the freezing point depression, and the osmotic pressure. These are the 4 properties we're going to study. We're going to take them pretty much in that same order. Let's start out with the vapor pressure lowering. So let's take a simple scenario. Let's say that I have a volatile liquid solvent. Remember, volatile means a liquid that is easily vaporized. And I'm going to dissolve a non-volatile solute, one that doesn't vaporize. In other words, the vapor pressure that would be above this liquid solution is going to be due to the vaporization of the solvent only. So at 25 degrees, the vapor pressure of water is about 23.8 millimeters of mercury. But if I dissolve, let's say, 65 grams of glucose in 150 grams of water, the vapor pressure drops to 22.8 millimeters of mercury. The interesting thing about this phenomenon is not only that the vapor pressure is lower, but that there is a mathematical way of calculating what that pressure is going to be, and it's called Raoults Law. Raoults Law says that the vapor pressure of the solution is going to be lowered in proportion to the mole fraction of the solvent. And this is where we incorporate that unit of concentration that we barely touched on in the previous lecture, the first lecture, mole fraction. So here is the formula for Raoults Law. So in this formula, the P of solution is the equilibrium vapor pressure of the solution itself. X of the solvent is the mole fraction of the solvent. Remember, mole fraction means the moles of one item divided by the moles of all the items in the mixture. And then P prime or P naught solvent would be the vapor pressure of the pure solvent at that particular temperature. For example, in this case, if we're talking water at 25 degrees, the vapor pressure of pure water would be 23.8 millimeters of mercury. All right, so let me give you a few moments to write that down, make sure you got it. I think what's cool about this and all the other properties is that they are not purely qualitative observations. These have, pretty hard numbers associated with them. Cool. Okay, so let's do a little sample problem here. Question: what will be the vapor pressure of a solution made by dissolving 218 grams of glucose, and there's the molecular weight of glucose, 180.2 grams per mole, in 461 grams of water at 30 degrees Celsius? Let's say the vapor pressure of water at this temperature is 31.82 millimeters of mercury. Okay, that's our question. So let's bring in, since we're talking about vapor pressure and we're talking about temperatures, and we're going to be talking here about a solution, we're going to use Raoults Law. So just like in other problem-solving exercises in the course, a lot of the key of these things is identifying what do they give me and what do I need to find out and what are they asking for, right? So they are giving us this value. This is the pressure of water at this temperature, right? We have it there, 31.82 millimeters of mercury. So what we're going to have to do is we're going to have to calculate what is the mole fraction of water. Remember, this is the solvent. not of the solute, so that we can find the vapor pressure of the solution. All right, so that's our strategy. So with that in mind, let's go ahead and put in the numbers here. Start out by figuring out the mole fraction of water. Well, to do that, I need to find out, well, how many moles of solvent and how many moles of solute do I have here? So let's start out with the water. They told us that I have 461 grams of water. And by now, guys, you probably have memorized the molar mass of water, right? Because you've done it so many times. So H2O, 2 hydrogens and 1 oxygen, that's 18.02 grams in 1 mole of water, right? Let's make sure the grams of water cancel out. So now we have the moles of water. Just do a quick calculation there, do 3 sig figs, because that's what the grams of water have. So we had 25.6 moles of water in this sample. Okay, let's calculate now the moles of glucose. And I didn't want to bother you with calculating molar mass. I gave it to you the molecular weight. So we had 218 grams. They told us over here that 1 mole is, that's right, 180.2 grams. We can cancel out the grams of glucose units, and we're left with moles of glucose. And result is 1.21 moles of glucose. So the reason we did this was because, remember, our first task was going to be finding the mole fraction of solvent. That is moles of water divided by the total moles in the solution. So the pressure of the solution would be the mole fraction, which is the moles of water divided by the total moles, water plus glucose, times P naught, which is the pressure of water pure at the same temperature. And that gives us 30.4 millimeters of mercury. Okay. Excellent. Okay, so we have a phenomenon called the vapor pressure lowering due to the presence of a solute. We have a formula, Raoults Law, that allows us to calculate this. And obviously, you could turn this around. I could tell you, well, if I have a solution made with, water and glucose, and I have the vapor pressure that I measure is this, but the vapor pressure at that temperature should be this other thing. What is the mole fraction of water in here? You could solve for X, but normally what we solve for is the predicted vapor pressure. So it all depends, okay? Now, like everything else, we'd like to have an explanation for this. And you see there on the heading where we're going, right? That's right. We have an observation of matter, that is the vapor pressure of a solution. And now we had to bring in our other 2 actors here, energy and entropy. Remember this model that I sketched out for you last time. Remember that we're proposing that the path to making a solution is step 1 and 2, you essentially break up interactions between solvent molecules and between solute molecules. And then you form new interactions as you make the solution, right? So we said that in the solution, you have new solute-solvent interactions. And remember, when we say interaction, we're typically we're talking energy, right? Remember that when we talk about things that attract each other, the energy has to do with how close or how far those particles are to each other with respect to the force that attracts them. It's potential energy. It's the energy due to the position of particles with respect to an attractive force. But the other thing you can see here, and this is perhaps more evident for the solute, because I deliberately started with a solute that was pretty highly organized, like a solid, is that in the solution, you can see where there is a new degree of randomness in the distribution of particles. This was that property that we learned about last time. We call it entropy. It's the degree to which the particles of a system are distributed more and more randomly. You can see here where my solute started out as a highly ordered, fairly limited set of distributions kind of substance. And in the solution, those solute particles, the red ones in here, are distributed very randomly. In other words, the solution proceeds with an increase in entropy. Now let's do some charts here so we can see what happens and the difference between a pure liquid and the solution. So let's start out with our solvent. Let's say that your solvent is pure, and what you're going to do is you're going to vaporize it. Notice that for the same reason we said that when the solute was dissolved in the solution, it became more random. You can see here a couple of things happening as you vaporize the liquid. Number one, the particles of the liquid have to overcome attraction forces in order to vaporize. Remember, vaporization is an endothermic process. You have to put energy in so that the liquid particles will kind of separate from each other against the forces of attraction that want to keep them together. So energy is required as an input in that process. Now, what about entropy? Well, I don't know if you noticed this, but in the gas state, and remembering the kinetic molecular theory we propose for the gas state, you can see where the molecules, the particles in the gas state, are more disordered. They're more random. They're distributed all over the place. In other words, if we were to look at the entropy change in here, we would say this is a process that increases entropy. And just like most things in nature, statistically, an entropy increase is typically a favorable entropy change. I'm going to draw it this way, and I'm going to use delta S. S is kind of the conventional symbol for entropy, just like E is for energy, right, and T for temperature and what have you. So the conventional symbol for entropy is S, and we're seeing here a huge increase in the entropy when the liquid is vaporized. Now, let's see what happens when I put a solute into my liquid solvent. In other words, when I make a solution. Well, first of all, notice that now, besides the liquid solvent interactions, you also have now solvent-solute interactions. So you're going to start by needing maybe a little more energy than you had with the pure liquid, because you have now two types of interactions to overcome. Some molecules have to be pulled away from each other. Some of them have to be pulled away from the solute. Again, remember that in this scenario, we're considering that the solute itself is not going to vaporize. Don't forget that. All right. Now, what did we say about the solution? We said that in the solution, your entropy is already a little higher, right? We said that the entropy of a solution is slightly higher or quite higher than the entropy of the pure liquid, because you have essentially randomized a lot more the distributions of particles in there. Now remember that in our example, only the solvent is going to vaporize. So the solvent is going to achieve the same state as it did on the left side there. In other words, you have a certain amount of entropy increase. But notice that because you started at a level of entropy that was already a little on the high side, the entropy change that happens now is smaller. In other words, it's a less favorable delta S, a less favorable entropy change, right? So that means that now in the solution, the molecules of the solvent are not as enticed, let's say, or stimulated or motivated. I'm talking like these things we're thinking about them for themselves, but anyway, just you get the idea, right? They are not in a position where the entropy change favors vaporization that much, and therefore, between the extra attractions in the solution and the less favorable entropy change, you can see where less of the solvent molecules will vaporize, and as a consequence, you will have a lower vapor pressure above the solution. All right. So hopefully those sketches helped you out. If not, we'll have a little break in a moment. You can ask me questions. So this example that I gave you, all of it is dependent on the solute not vaporizing. But of course, we have many solutions where both components are soluble. I mean, think about solutions of, vinegar, where both the water and the acetic acid could vaporize. What about solutions of alcohol with water, where both of them can vaporize? So let's see what happens if I have two volatile components, both the solute, quote unquote, and the solvent. And remember that many times, particularly when we mix liquids, the designation of who's the solvent and who's the solute is somewhat arbitrary, because usually liquids, if they are soluble, we say they're miscible. In other words, they combine in all kinds of proportions. So let's consider a mixture of benzene and toluene. These are two compounds that are they are not water soluble. So we're going to mix them with each other. They're both nonpolar compounds, so they dissolve fairly well in each other because they share similar kinds of London dispersion forces. So let's say that we are going to do this graph here. Notice that we are plotting the vapor pressure as a function of the mole fraction of benzene, right? So when you start with 0 benzene, right? So essentially, what you start with is, this would be the vapor pressure of pure toluene with no benzene added. Everybody understand that? Okay. Notice that as I begin to add toluene in this case, as I begin to add benzene in this case, of course, what I'm doing is I'm changing the mole fraction. So the total volume is the same, right? The total volume of liquid is the same. We're not simply adding benzene. We're switching some moles of toluene into moles of benzene. So of course, the vapor pressure respecting toluene decreases, and the vapor pressure with respect to benzene increases. Now, if I were to add, excuse me, the vapor pressure of one plus the vapor pressure of another one, I notice that at the end of this process, when there is essentially just benzene and no toluene, I'm going to end up over here at the top. You can see it there where I'm kind of like highlighting. I'm trying to highlight here. Hold on. Right there at the end. At that point there where the mole fraction of benzene is 1, that means that is where the vapor pressure is just the same as the pure benzene's vapor pressure. But in the process, if I'm adding the vapor pressures, what I find is this solution, both components obey Raoults law, and you get a straight line in there. This is what we call an ideal solution. Again, it's a solution where each one of the components obeys Raoults law, and therefore the total vapor pressure of the solution is simply the sum of the partial pressures of each one. Now remember, one of them is going to have a partial pressure that will be following Raoults law, so mole fraction of A times the vapor pressure of pure A. And then for component B, let's say benzene, that would be the mole fraction of B times the vapor pressure of pure benzene. And according to Dalton's law, you would have the total vapor pressure would be the sum of the partial pressures of each. But since each one obeys Raoults law, you have this expression here. So why am I going through this? Well, obviously, if I'm calling it an ideal solution, it gives you the sense that probably there must be some that are non-ideal. And that is the point. If I run an experiment where I plot the vapor pressure of a mixture of two liquids against each other, and I find that the vapor pressure essentially is directly related to the sum of the partial vapor pressures, and the partial vapor pressures, each one follows Raoults law for each one of the components, then I have what's called an ideal solution. And the explanation for that has to do with the observation, or let's call it the deduction, that essentially when you combine these things, although they have interactions with each other that allow them to dissolve in each other, they don't get in each other's way when it comes to vaporization. So unlike the chart that I showed you before, the vapor pressure here is lowered, but only in proportion to the mole fraction of that particular liquid. The presence of the other liquid doesn't really have an impact. Now, we do have what we call non-ideal solutions, right? In other words, this is a solution where the total vapor pressure does not correspond to the Raoults law derived vapor pressures for each one of the components. Now, I'm going to let you guys read this in your textbook and look at some pictures, because in the interest of time, I'd like to kind of skip a little bit of the deeper explanations. Bottom line, here's what happens. Let's say that although these two components form a solution, the solute-solvent interactions are very weak. It's almost as if, let's say, yeah, they kind of put up with the other liquid molecules being there, but it's not like they're really fired up about it. And if they get a chance to skip the party, they will. And so what happens is that because those interactions are not that strong, the liquid simply vaporizes, not in proportion to its mole fraction, with perhaps a little more than its mole fraction. And so as a consequence, the total vapor pressure is actually higher than predicted. So, if you do a graph of that, and you can see this in your book, if you do the graph that I showed you before, what you're going to see is that instead of a line, you're going to get like a curve that goes like that. In other words, the vapor pressure is going to go kind of like above where you would expect a straight line to go. Until, of course, when it reaches the mole fraction of 1, where you have only one of the components, of course, the vapor pressure will be whatever it's supposed to be for that pure liquid. The other scenario you can have is that if the interactions between solute and solvent are very strong, in other words, these guys, when they mix, they really like each other. And because the solute-solvent interactions are so strong, it keeps the molecules of the liquids from, vaporizing that easily. And so as a consequence, the total vapor pressure ends up being lower than predicted. And again, if we look at those graphs, what will happen is, again, if this is the pressure here, right, on the left, and this is the mole fraction of one of the components. What you're going to get is that instead of, let's say, the straight line of an ideal solution, you're going to have a curve that kind of goes underneath there. I'm sorry for my bad drawings here. You know what? Here's what I want you to do. Why don't you guys go ahead and in your TRO textbook, if you have the 5th edition, just look at the charts in figure 14.15, all right? I think in the 4th edition, this would be probably 13.15. And in the 3rd edition, 12.15. It's .15. Whatever the chapter is for solutions, that's the picture. And they have some nice pictures in there and some probably better explanations than the ones I'm giving you. But this is pretty much what you need to know. Okay? All right. Well, let me do this here. Let's go ahead and pull out of there. And let me see if anybody has any questions. We're going to take a 10-minute break, and then we'll come back and talk about boiling point elevation, freezing point depression, and osmotic pressure. Does anybody have any questions? You might still be writing things down. So just go ahead if you have any questions. We're going to take a break now. So let's go ahead and